Hey, good day. Today you will be learning about two scheduling strategies, the first come first served and the round-robin scheduling. A scheduler has to make a decision of what process should be sent into the CPU next. This decision has to be made according to a set criteria. Maximize the system throughput, provide tolerable response, be fair to all users, be consistent and predictable, and it should be maximized. Waiting time and response time should be minimized. Actually, we have 4 approaches to CPU scheduling, but for now we'll just talk about the first come first served and the round robin. So first come first served, also known as first in first out. This policy assigns the processor to the process which is first in the ready queue. It has been waiting for the longest time. This is used with non-preemptive operating systems. The response of the system is not dependable. First come first served favors long jobs over short ones. Here's a short scenario. Hooray! I could stay here forever. Anyway, I'm not going back to the end of the queue.
Hurry up. You've been on that processor for ages.
Look at the size of the queue. Sorry, first come first served. Round robin. This is first come first served with preemption, where process is given a finite time slice on the processor. The queue is circular, thus when a process has been run, the queue pointer is moved to the next process. This is a smooth schedule and gives all processes a share of the processor. Here's a short scenario for round robin. Okay, number 1, you had your turn. Get to the back of the queue. Okay, next.
Come on. My turn soon.
Still confused? Here's another one for you.
For the rest of today, and I think the rest of the class, we're always going to be focusing on on-demand schedules, where we don't know all the tasks in advance. We have tasks coming in. We may have tasks with deadlines. We may have tasks that don't have set deadlines. It's something that the scheduler has to determine on the fly. So the most obvious scheduling strategy is what's known as first come, first serve. So the strategy there, tasks come in. Here's the supervisor, the kernel. When a task is created, it gets added to some queue. Each time a task gets created, it gets added to the bottom of that queue. When the scheduler has a chance to schedule a task, it's always going to pick the first one. And that first one's going to get to run until it finishes. When that task finishes, then the scheduler is going to pick the next one in the queue. We're going to be executing the tasks in the order that they were requested. How well do we like first come, first serve scheduling? There are 2 properties we care about. We care about maximizing resource usage and fairness. How well does it do on those? Yeah, not that good. On both or on either? So some tasks are going to wait for a long time. Sounds like it's not doing too well on fairness. Fairness is a pretty tricky thing to define, but it seems pretty unfair if some task has to wait forever for a previous task to finish. How well does it do on resource maximization? Yeah, so it's doing really well on resource maximization because it's not wasting any time switching. Do we need a kernel timer interrupt if we use first come, first serve? The kernel can start a task. It doesn't need to set a timer. It lets that task run until it's done. That's really using our resources well. We're not wasting any time switching. We're only switching when a task is done and we're ready to run a new one. So the way this would work more in practice, tasks don't usually finish before their time is up. They usually get stuck. They're waiting for some I/O event. They've done a read from memory or read from the disk or some network event. They go back to the scheduler. They don't waste the processor waiting for that. If you really waited till the task totally finished, that would be bad for resource utilization because you're sitting around waiting for these I/O events. But as long as you're not doing that, you're not doing any unnecessary switches, and you're making good use of the processor. This is really the same thing as non-preemptive multitasking. It's saying once you've started a task, it gets to run until it gives up the CPU. One alternative is to say, we're going to give everyone a share. The kernel is going to have a list of tasks. It's going to set a timer. Every time the timer goes, it's going to switch to the next task in that list and go around the list, giving each one a fair slice. If a task stops on I/O, well, then it goes right away to the next one. So we're going around. In this case, we had 3. The scheduler is round-robin scheduling, giving each one a turn, and then giving the next one a turn. How do we like this? Yes. Okay, good. Yeah. So this definitely seems more fair. We're giving each process an equal share of the CPU. We're spending a lot more time in switching. When P1 is running, it gets to run for some time slice. And when that time slice is done, even if P1 is still doing useful work and has lots of more useful work to do, it's getting switched out, experiencing all the costs of doing a context switch, even though P1 could have kept running in a useful way. And that switch is very expensive. These are our 2 most basic options for scheduling. We've seen that first come, first serve is great for resource usage, and round robin is great for fairness. But they're both pretty poor for the other properties.
That's all for now. I hope you understand the lesson today. Thank you and God bless us all.